Okay, guys, continuing our little lesson on vectors and some of the investigations that go on with vectors. Um, we want to pose this question: how much of one vector is pointing in the direction of another? So down here I've listed two vectors, the red vector and the blue vector. The blue vector is intentionally drawn horizontally, so it's pointing only in the x direction. It has no y component. All right, so what we want to look at is how much of one vector is pointing in the x direction of another. First thing we want to talk about is direction. And just a reminder that direction is if we start at the x-axis and wrap around until we hit our vector, that's going to give us a direction. So thinking about this blue horizontal one, vector, we would have a direction of 0 degrees. That would be a horizontal. This direction, we would draw our axis about right there, and we wrap around until we hit our vector, and our direction with regard to the red vector would be theta. So we've got our general sense of what our directions would be. The other thing to kind of consider here is we know that this red vector here, if we write it in component form or as a position vector, we would be traveling a certain amount in the x direction and a certain amount in the y direction. And so we would have these different components that would make up this particular red vector. So we would have a component that travels in the x and looks something like this, and a component that travels in the y and looks something like this. So it's got an x and a y component. This one here would only have an x component that makes up the particular vector. So going back to our original question, how much of one vector is pointing in the direction of another? We want to take into consideration that any vector that's not perfectly vertical or horizontal is going to have an x and a y component, and that's what we kind of want to look at. So let's look at this from that perspective. I take my red vector, and we want to plot those essentially from the same initial point. And when we do that, we've got something that looks like this. So how much of one vector is pointing in the direction of another? Well, the direction of this is in 0 degrees. So how much of this red vector is pointing in the direction of 0 degrees? We would take into consideration our components here. And what we're left with is something that where we draw our vector, and it looks something like this. The horizontal component of that red vector would look something like that, where if we drew a vertical line down, we've got something that looks like this. So the question, how much of one vector is pointing in the direction of the other vector? This much. That's your answer. So this is the quantity that we're looking for. It's this much. That's in the x component in the same direction as the blue vector, and that's what we're going to set out to find. Okay, guys, so what we want to do is we'll just throw some labels in here. We'll call this vector v. We'll call the blue one vector w. And we'll call this quantity here that we labeled, we'll just call it quantity x. And this is our direction of vector v. So we'll label that theta. So a couple things that we know. We know, number one, that this is a right triangle. So we can go and write a couple of relationships that we know. So first of all, because this is a right triangle, we know that we can use right triangle trigonometry on it, or SOHCAHTOA. So in order to kind of figure out what this quantity is, how much of this vector v is pointing in the direction of vector w, we can use our trig relationship. So here's our reference angle, that's theta. We know that this quantity is going to be the adjacent side relative to that reference angle, and my v, this vector v, now it's not vector v in particular, it's actually the magnitude of vector v, is going to relate this length to this length. So we're looking at the magnitude of vector v in order to write our trig relationship. That's going to actually give me the distance, so I can write my ratios. So that's what I want to use. I want to use the magnitude of vector v, and we can go down here and write down our relationship. So we know that's the adjacent to the hypotenuse, so that is the cosine function. So cosine of theta, however big my angle is, I know the ratio of the adjacent to the hypotenuse is going to describe that or is going to be dependent on how large that angle is. All right, so x is my distance that I'm trying to find here, and the magnitude of v is going to be the distance of the hypotenuse, or the length of the hypotenuse. So what I'm interested, again, how much of one vector is pointing in the direction of another vector. I'm interested in this, and we call this a projection. It's a projection of vector v onto vector w, and that will give us the answer to this question, how much of one vector is pointing in the direction of the other. So we call x the projection of v onto w. And we can use what we wrote to kind of come up with a really simple expression in order to find that. So projection of vector v onto vector w is what we're trying to find in order to answer this question. And we can simply solve, and we know that the projection of v onto w we can find by taking the magnitude of v, so how long v is, and multiplying it by the cosine of whatever our angle is. So a couple things to recognize about this, this projection of v onto w. Number one, it's dependent upon how long vector v is. Okay, so the length of vector v is going to factor into this, and we can kind of think about that in general terms. What happens if maybe we've got a vector that is a little bit shorter than v? Well, what that's going to do is it's going to shorten the projection of v onto w to this length right here. Okay, if you lengthen that, then maybe that's going to extend v out to something that, you know, extends out to here, and we would drop a line perpendicular, and now my projection of v onto w would be a little bit longer. So it's dependent upon the length or the magnitude of vector v. The second thing is it's also dependent upon the angle between the two vectors. So we're looking at theta, that's the angle between the two vectors. If we kind of widen that angle, then what happens, or increase I should say, then what happens is it gets a little bit steeper. And what happens to the projection? Well, we drop a line straight down, and now my projection gets much smaller. Now my projection is only this amount. And so the bigger the angle here, it's going to shrink that projection. If you shrink the angle, so if you decrease theta, we're going to flatten that vector there, the green vector, trying to keep these the same length so it gives you a general sense. Well, that's going to lengthen that projection of v onto w, therefore increasing this overall quantity. All right, we go down to, I've got a little GeoGebra app here that'll kind of show you what's going on. So again, we'll just look at these things, and we'll keep this vector horizontal. So what I want to do is just change the angle here. So if I shrink that angle down of this vector here that's listed as v, if I shrink that angle, then my projection looks like this. Here would be my projection of v onto u in this case. U is our horizontal. All right, if I change that, and I move my my vector b and increase the angle, then again, we're going to drop a line straight down in order to look at the projection of v onto u, and this would now be the projection of v onto u, or the amount of that one vector, vector v, travels in the direction of the other vector u.